One of the most important concepts in computer science and in algorithm design is the notion of data structures. Data structures. All algorithms deal with data, and this data has to be represented in a structure that stores the data and relationships among the data points as well. And these structures that represent the data plus a set of operations that we implement on top of that structure is what we call usually the data structure. Okay, so the data structure, sometimes also called, for some, if we think about it in more general terms, it's ADT, abstract data type, is we need to think about the structure itself. The structure itself, is it an array? Is it a list? Is it what? And we need to think about also a set of methods or operations. Okay, what do I mean by that? For example, minimum, right? So we want to find the minimum in the structure, the minimum element in the structure. We can define maximum as well, and so on. Okay, so when we talk about data structure, we want the structure itself. How are the objects in the structure connected to each other? And then we have a set of operations that we want to implement on top of that data structure that allows us access to elements in this data structure, as well as any other operations that we want to do. Now, one important point to mention from the beginning about data structures is that data structures are in general there to represent sets. Okay, so we have basically sets, which are collections of elements with no order on them in general. And we want to store these sets of elements. So the set of all students in my course, or the set of all flights of an airline, or the set of all employees at the company, and so on. These are sets that we want to basically, when we enter information about them in a computer, or we want to have a program that analyzes them, they have to be represented in a structure. So in computer science, unlike math, the sets are dynamic in most cases. Okay, so when we talk in math about sets, mathematicians talk about the set of all reals or complex numbers or natural numbers. These are sets, fixed sets. They are not dynamic sets that you can add to them and remove from them. In computer science, we typically work with dynamic sets that we can add to them, we can remove from them, we can update elements in them, and so on. So please keep this in mind when you're thinking about data structure. A data structure is most often for representing the elements of a set. Okay, and what makes the design of data structures interesting is the set of operations that we want to implement, because we want this set of operations. First, we want sometimes specific way of accessing the elements. Two, we would like for this set of operations to be efficient, right? And efficiency of a certain operation basically dictates the design of the data structure. And let me say up front that if the data structure is inspected, or an operation is applied on the data structure once every 5 years or something like that, then we should not bother with efficient or with elegant design of the data structure. Same thing also for very small amounts of data. If our set has 15 elements, it's not going to matter really what's the design of a data structure, because you can scan the 15 elements in almost no time to find the minimum, the maximum, do whatever you want with them. So our focus is always about, okay, data structures on sets of n elements, and we want the performance of the operations on these data structures to be good as n grows large. Okay, now some basic data structures that have been seen by most students at this point are stacks and queues. So these are some elementary data structures. So we have the stack data structure and we have the queue data structure. So what is a stack? We have basically a representation of the data where the data is inserted into the data structure and removed from a data structure in a very specific way. In the case of stack, it is last in, first out. Okay, so LIFO. This is the case of stack. So whatever The last element to be put on top of the stack, is the first element to be removed from the stack. And again, think of it, the best example of it is a stack of trays at a cafeteria or at a restaurant. The very last tray that was put on top is the very first tray to be used by a customer. Okay, so if I put, for example here, the first element I put on the stack is 2, then I put 10, and then I put 11. If someone asks me to get an element out of the stack, the element I will get out of the stack is 11. I have no choice. I cannot go to 2 or to 10. If I want to go to 2, I have to remove 11, I have to remove 10, and so on. Q is, if you think about the cafeteria again, it's like the line of customers, or the first person to enter the line is the first person to receive service at the restaurant or at the cafeteria or at the bank, and the first person to leave the queue. So if we think about the queue like this, and again we put 2, then 10, and 11 enter. So this is, here we can think about it as the tail of the queue, and here is the head of the queue. They always enter, the elements enter at the tail and they exit from the head. So 2 was the first element to enter, it's the first element to exit as well. Okay, so here we here the system we have is first in, first out. Okay, the first element that went in is the first element to go out here. And these are two data structures that we can, for example, represent with arrays, right? So I can, for example, if I want to represent a stack with an array, suppose I have a maximum 50 elements can be on a stack at most. Suppose the restaurant doesn't have more than 50 trays, then I can define an array of 50 elements, for example, and the array will be like this. This will be here the last element in the stack. This is the last one, or the top of the stack, and this is the bottom of the stack. Okay, so here if we talk about this, the top of the stack. So if I go back to that example of 2, 10, 11, 2 will be here, 10 will be here, 11 will be here. And we always have access to the very last element on top of the stack. Okay, we can do a similar implementation for a queue. And you will immediately notice a problem with this array-based implementation. As I said, I have an array of size 50. I have decided that I have 50 elements in this array. Why? Because I assumed that this is the maximum number of trays. What if the restaurant now has ordered new trays, and now they have 100? What do we do with this array? Right? I cannot represent more than 50. I cannot put more than 50 items in a stack for which I have already declared that I have 50 items in it. Another problem with an array implementation is that, look here, if I have 3 elements on this stack, I have allocated memory for 50 items. So 47 items in that array are unused. So we have wasted memory. So an array is very rigid in that sense, that you have to define, once you declare the array, you have to say how much memory, how many elements you can put in that array. If you want to exceed that number, you run into a problem. But also another problem is on the other side of the spectrum here, is that if you don't use many of the items in the array, you are wasting so much space. And this is what leads to the natural representation beyond array, which is linked lists. If you think about linked lists, it's also a list. It's a list or data structure that stores objects in a linear fashion. Okay, so the objects appear in a linear fashion. So we have an object and the object before it and the object after it. This is what I mean by linear. So if you point to an object, you ask me what's before it, it's a well-defined question. What you ask me what's after it, it's a well-defined question. So a linked list, instead of defining an array of 50 elements and I'm using only 3, I can actually say, okay, since I have only 3 items, I can declare 3 objects, each of which is going to have these keys 2, 10, and 11. Now, in addition to that, we have, in this case, for example, I can define 2 pointers. One is going to point to the parent, one is going to point to the child, or one can point to the predecessor. So when I look at the linked list, every object, in my case here, will have a key and will have a predecessor and will have next element. Okay, so if I, or previous and next. So here, this is the previous element in the list, this is the next element in the list, and this is the key that's stored in that object. So if you look at these three objects that I put here, that the first one has the key 2, the second has key 10, the third has key 11. And then I can say that the next after 2, it points to 10. Okay, so it points to this one here. And next after 10 comes 11, it points to this one. Now, the previous of 10 is the one that has key 2, and the previous of 11 is the one that has key 10. What about next for the one that has key 11? What about the previous for the one that has key 2? Since there is no previous to 2, then we basically, this points to nil, okay, or null, or whatever we want. Basically, it's pointing to a specific or a specific object that we call nil. Okay, there is nothing there. The same thing with this one here. This points to nil. So this is a linked list. Now, the linked list here in this case, for example, I have 3 objects. Suppose I want to enter I add a new one. Again, I'm not talking about sorted list here or anything like that. So if I want to enter a new element here, I can enter it, for example, if I think about I have a pointer to the beginning of the list, and 2 is the first element, first object in the list. And suppose I want to enter a new element with the key 7, then all I need to do here is that I can come and define a new object. I can define a new object with key 7, and now its next is the one with 2. Now 2's previous now changes from nil, it becomes this element here. Now 7 has no previous, so this is nil. And now when we talk about the list and we are talking about access to the list, now the access is to this. This is the first element here, the one with key 7. Okay, so if you think about this, it takes really a constant number of operations to add to a list. Once you give me an element and you say add it at the front of the list, for example, and we have a pointer to the front, it's one operation, a constant number of operations, or of one. Suppose you give me an element and say I want you to delete this object. So suppose you come and say I want you to delete the object with key 10. I want you to delete this one. So you are pointing to it. Okay, you are not asking me to search for it and remove it. No, you are giving me a pointer to it and say remove it. Also, it takes a constant number of operations to remove it, because all I need to do is that I can delete the item here. I can make the next of 2 to be this element here, the one with key 11, and I can make the previous of the key with the one with key 11, the 2 here, and we are done. So this is gone now, and I have no issues that we ran into with arrays. Okay, so if you think about it here, I can do in O of 1, I can do deletion and addition to a linked list. And one nice thing about a linked list also is that I don't have any waste of memory. I don't have any bound on the memory in theory, right? I mean, of course, the memory on your computer will bound everything, but in theory, I can enter a number of elements here because I can keep adding to it. And there is no wasted memory here, because I have the number of objects that exist in the linked list equals the number of objects we really need. Okay, I'm not going to be wasting 47 positions in an array because I have declared an array of size 50 and used only 3. Now, this notion of linked list and the notion of not wasting memory, this has to do with how we allocate memory and free memory. So some systems have what we call garbage collection. Garbage collection is this system for taking care of allocating memory when you need to add one, to create a new object to add to the list. That system will allocate the memory for you. When you delete an object from the list, that system will take care of also freeing the memory that was used by that object. Now, one thing to keep in mind about linked lists is that if I want to search for an item in this linked list, for example, if you tell me, here's my linked list, can you find if the element 17 is in it? Well, it's going to be the running time of such an operation is going to be O of n if the linked list has in objects in it. Okay, so if the linked list has in objects like this, and you give me a pointer to the first element here, and you say, can you find if the key 17 is in this list? I will check the first one. If it's not there, I move to the second one. If it's not there, I move to the third one. In the worst case, I have to check all of them, and by the time I finish the entire list, I don't find it. So worst case running time of searching for an element in the linked list is O of n, okay? And implementing such an operation is very, very simple. You just, you have a pointer to the first one, you say, is the key equal? If not, now you go to next of that pointer, okay? If not, you go to next of next, and so on. So these linked lists are very, very dynamic. They allow us to allocate the amount of memory that we need to use, nothing more and nothing less, okay? And we can extend these linked lists by adding more pointers to them. We can, for example, make the linked list circular. How do we make it circular? If you make, for example, the next of the, once we go to circular, there is no first and last, but if you look at this linked list here, and I label them as the first object 1, object 2, 3, all the way to n, if you make the next of n to be the first one, and if you make the previous of the first one to be the last one. So now this is circular linked list, because you can actually keep going back, you can go in a circle on this linked list, going from an item to the next, to the next, to the next. At some point you go back to the same object, and you can keep doing that as much as you want. So this linked list, I can actually increase the number of pointers, and for an object I can point to 2 elements, I can point to 17 elements, whatever I want. One specific structure that we care so much about is the notion of binary trees, rooted binary trees, okay? So rooted binary trees. What does it mean to be rooted? There is a specific node in the tree that is the root. The root is unique, okay? So we cannot have more than one root. What does it mean to be binary? A node cannot have more than 2 children. It can have 1 or 0 or 2 children. And tree means that the graph we are looking at is acyclic. We don't have cycles in it, okay? So here's an example of a rooted binary tree. Something like this, okay? This is the root here. This is the unique node that is the root. Every node has 1, 0 or 1 or 2 children. So for example, for this node 1 here, it has 2 children that are 2 and 3. 3 has 2 children that are nodes 4 and 5. 5 has one child, that is node 6 here. 6 has no children. 4 has no children. 2 has no children. So how would we represent a rooted binary tree using similar thing to what we showed, for example, for linked list? So now if I think about a node, if I think about an object here, I can think about the object has four items in it. So we have the key itself in the object. So here, what is the value there? For example, if the binary tree is storing the grades of the students, the key would be a grade of a student. If the tree is storing the student IDs of the students in my course, a key would be a student ID. Then we have here parent. This is parent pointer. So what is the parent of this node in the tree, or of this object in the tree? Then we have left. So we have a pointer to the left child, and we have a pointer to the right child, okay? So this is how every object would be to represent a rooted binary tree. So for example, suppose I have the set of elements 2, 5, 10, 14, and suppose I put them in a data structure like this, for example. So I have the K2 here, and one child is, for example, I have the key 5, and the right child of this is going to have the object with the key 10, and let's say the right child of this is going to have 14. Okay, so this is going to have 14. And what happens with all the other pointers here? Okay, so we have these pointers. So the parent of the root is nil. Okay, so the parent, the root has no parent by definition of that. The left of the root again goes to the key 5. The right child of the root goes to the one with key 10. The parent of 5 is the root, so it points to this object. The parent of this points to the root as well. This one here points to nil, no left child, and this is nil, no right child. This one points to nil, no left child. This one here points to nil, and the right one points to nil. Okay, so this would be a representation that goes beyond linked lists. So we don't have a linear structure anymore on the items, and we have a tree structure on it. But all we really needed to do is to define for every object 3 pointers. 1 points to the parent in the tree, 1 points to the left child, 1 points to the right child. If we wanted to allow the trees to be more than binary, for example, they could have 5 children, then we define more than 2 pointers. We can define 5 pointers. If the number of children is dynamic, that we don't know a priori what's the number of children, then the pointers to children can themselves be a linked list. So imagine that you have a linked list of pointers to the children. That way we can allow the number of children to vary from one node to another. And this kind of structure here is what we call a binary tree. Okay, so in the case of data structures, when we are talking about binary trees, unlike when we define binary trees on graphs in general, here we are talking about rooted binary trees. So we have a root, and then we have children. Okay, so there's the root, there are the children of the root, and then there are children of the children, and so on. Just in terms of terminology, just like we talk about children and uncles and grandparents and so on, we can use the same terminology also. We can use the same terminology also on binary trees. So for example, if I have this binary tree here, and let me label them nodes 1, 2, 3, 4, 5. So 3 is 5's parent. 3 is 5's parent. Okay. 4 is 5's sibling. Okay. 1 is 5's grandparent. Okay. We can talk about 2 is 5's uncle. Okay, so if you think about 2, it's the sibling of 5's parent. We can talk about it as uncle. Again, we use the word uncle. We can use aunt, whatever, but you get the idea here. Okay, so these terms are helpful when we start talking about binary tree data structures, because we need sometimes to refer to the sibling, to the uncle, to the grandparent, and so on.